A space elevator is a theoretical structure designed to transport payloads from Earth's surface to space without the need for traditional rocket launches. The concept involves a long tether or cable extending from the surface of the Earth to a counterweight in space, such as a geostationary satellite. The tether would be held taut by the rotation of the Earth, allowing payloads to travel up and down the cable using climbers or other propulsion systems. Key features and components of a space elevator. Tether or cable. The primary structural component of a space elevator is the tether, which extends from the Earth's surface to space. The tether needs to be strong, lightweight, and able to withstand various environmental conditions, including atmospheric effects and micrometeoroid impacts. Counterweight. A counterweight is placed at the upper end of the tether, often in geostationary orbit. The gravitational forces between the Earth and the counterweight help keep the tether taut. The choice of a geostationary orbit ensures that the counterweight remains stationary relative to a point on the Earth's surface. Climbers or transportation vehicles. Payloads or spacecraft would travel along the tether using climbers or other transportation vehicles. These vehicles could use mechanical means, such as wheels or treads, or employ propulsion systems for vertical movement along the tether. Earthport. The base station on Earth, often referred to as the Earthport, would serve as the point of departure and arrival for payloads and climbers. It would include infrastructure for loading and unloading cargo, as well as the systems necessary for launching and receiving spacecraft. Potential advantages of a space elevator? Reduced cost. One of the primary advantages of a space elevator is the potential for significantly reduced transportation costs compared to traditional rocket launches. The elimination of the need for large rockets and fuel could make space travel more economically viable. Accessibility to space. A space elevator could provide a continuous and reliable means of accessing space, making it more accessible for various purposes, including satellite deployment, space tourism, and space exploration missions. Reduced environmental impact. The use of a space elevator could potentially reduce the environmental impact associated with traditional rocket launches, including greenhouse gas emissions and the depletion of finite resources. Regular and routine access. The availability of a space elevator could enable more frequent and routine access to space. This could lead to increased scientific research, exploration, and commercial activities in space. Technical challenges and considerations. Material strength. Developing a material strong enough to support the immense tension along the entire length of the tether is a significant technical challenge. Carbon nanotubes and other advanced materials have been proposed for this purpose. Geostationary orbit placement. Placing the counterweight in geostationary orbit requires precise orbital positioning. Achieving and maintaining this positioning is a challenging engineering task. Environmental hazards. The tether would need to withstand various environmental hazards, including atmospheric conditions, lightning, and micrometeoroids. Adequate shielding and protection mechanisms must be implemented. Regulatory and legal issues. The deployment of a space elevator would raise regulatory and legal questions, including issues related to airspace usage, international agreements, and liability in the event of accidents. As of my knowledge cutoff in January 2022, the concept of a space elevator remains largely theoretical, and significant technical and engineering challenges must be overcome before it becomes a practical reality. Research and development efforts are ongoing, with advancements in materials science and space exploration contributing to the ongoing exploration of the feasibility of space elevators.